Hey guys, thanks for tuning in to this third episode of BCI 101 Basics of BCI Hacking. We will be building a neurofeedback paradigm using the alpha wave signal that we saw in episode 2. Just a quick reminder, episode 1, I introduced the Muse 2 as a BCI hacking device of choice. It's a device that is accessible. In episode 1, I showed a few signals, the way they show up when you first put the Muse. And what you get in terms of the EEG signal, or at least the biometric signal sensed through electrophysiology sensors. Episode 2, I showed a first experimental paradigm called capturing the alpha wave, where I showed that the alpha wave emerge when you close your eyes. So eye open, eye close, you will see the alpha wave coming up in the EEG signal. And now episode 3, for those interested in brain-computer interfaces, it's probably where the fun begins because we are working towards a neurofeedback application. I try to bring them in the field of entertainment. This is where I operate most of my brain-computer interface hacking. So we'll look at how we design an experiment. Today we will do some offline design in terms of like what we want in terms of experiment, a few simple model of how to capture the feature that will be used for the true online paradigm. So the objective for today, I want to introduce biofeedback experience design, introduce parametric modeling, what we'll be using to model the features that we'll be using for the real-time paradigm. We'll demonstrate offline validation process. How do we use offline data to build a model, build and model the features that will be used for the real-time operation? And part 2, which will be the next video, will demonstrate a basic real-time paradigm where we have neurofeedback taking place using the alpha wave. First part, experience design. This motto here, one that I love a lot, is necessity is the mother of invention. I'll come back to this in 2 slides. So in terms of biofeedback experience design based on the alpha wave, there's one thing that stands out, is that to trigger the alpha wave, you need to close your eyes. Now, this can be seen as a limitation because we want to provide some feedback to the user, but if eyes are closed, we can't use visual feedback. Now, we could see this as as something that is very limiting, some things that there's no way to work around. But if we use this limitation and see it as a challenge to develop something new, this is where I think that the necessity is the mother of invention. That is, instead of blocking on the barrier that eyes are closed, let's work around this limitation and develop something that is new. And I think this is something you need to take into consideration when you develop brain-computer interface. The technology itself is very limited, as a lots of limitation, I would say. And if you want to develop nice hacks and nice applications in the field of brain-computer interface, you need to be able to find barriers and step over them to discover new ways to use the technology. This is a absolute necessity if you want to thrive in that field. So let's see now. We want so just a parenthesis here. So we might consider the fact that we have eye close as a limitation, but here I pulled a bunch of examples from various sources. Like I said, I'm in entertainment to see how eye close can support some kind of narrative. You see here I have 2 samples, obviously, from Star Wars. We have Luke Skywalker when he wants to use the Force to lift the X-Wing in the swamp during his training. And he has his eye closed to show how he needs to be mentally focused. We have Rey here in training that also use the eye closed as a way to be more focused and align with the Force. We have Naruto here mixing the chakra during a battle. Imagine you have to stay calm during a battle to build this power that you can then use to cast spells or do some, in this case, some jutsu. We have here another example. This is Doctor Strange in the Marvel Universe, where his eyes are closed while he's, I wouldn't say he's mixing chakra here, but he's definitely casting some type of spells that require some concentration. And we have The Witcher here that needs to meditate to speed up healing and recover from a battle and some injuries. So you see, so the effect, now we already opened this door here, that the fact that eyes are closed is not uh, incoherent with some entertainment and experience. So the basic of biofeedback experiences is we're measuring EEG or any biosignals for that matter. Those signals are sent to a system that will interpret them and will generate some form of feedback, okay, that can be then taken into account by the user. So we need to provide this feedback. There are five senses, okay? There are other ways, but I mean, the basics is there are five senses. Now, the fact that the eyes are closed, we need to rule out sight. For this specific biofeedback experience, we cannot use sight. Then we have smell and taste, which we could technically find some ways to use smell and taste, but I'd say that for the current BCI one-on-one hacking, I'd say it's a little bit challenging to develop something using smell and taste. So it leaves us with touch and hearing. Now, in regard to touch, it's a little bit more complex, but there's definitely something super interesting that can be done. A few years ago, I developed a glove that was providing vibration, heat, and cold feedback to the hand, okay? And I actually connected it with the alpha wave. So the idea is that you could cast a fireball, and as your eyes were closed, you could feel the heat in your hand using that glove. Now, this hack is a little bit more elaborated than what we can do like quickly with the Muse and ear. So for today, we'll focus on earring. So we'll plan at least to provide some auditory feedback during the biofeedback experience. So this is the modality that we'll be using. This is the experience we'll be using. So people will, our user will wear the BCI headset, the Muse, and they will be provided with audio feedback. So now we have a goal of what we want to design, what we want to build. It's a good opportunity now just to interrupt you a little bit. If you want, like and subscribe. It's amazing. I mean, I've been building, obviously, I mean, anybody who starts a YouTube channel is obviously, it's a more of a hobby and more of a pleasure than anything else. But still, I've seen, even in the past few months, this channel growth and the feedback I get. I mean, it provides so much energy and so much encouragement when some people come say, hey, I really like your content and stuff like that. So like, subscribe if you want to leave some encouragement, or if you have any questions. I try to answer everyone. Like, subscribe, leave a comment, and let's move forward. So now we have a goal as to what kind of experiments we want to design. The auditory feedback, we'll get into it in the next episode, but for now we want to transform. We want to in the last episode, we saw the alpha wave. We saw it through frequency analysis. I'll bring back this graph in a few slides. But now we need to measure it, we need to detect it, we need to develop something that not only shows it on screen, but that makes it in real time, will make it possible to detect the alpha wave. So this is what we will be working on for this specific episode. I want to introduce, for some of you, parametric modeling. Parametric modeling is the idea that we use some machine learning algorithm that we fit some parameters to find some characteristic of the feature that will be used in the experiment. Another motto here: try simple things first. I don't blame it on anything, but I found I've been in the field of machine learning for a long time, and I found that recently people are quick to go straight to deep learning. I hope that through this episode you'll see that there are simpler models that are available and sometimes are very sufficient in terms of when you want to build something. So this is why I say try simple thing first. It's kind of a rule of thumb in machine learning. If a simple model can do the job, prefer a simple model over a more complex one. Modeling objectives here, we want something that is unsupervised. The challenge we have here is to build something that will extract the features of our signal, but we don't want to have our user go through some form of calibration, or at least not one that is explicit. So we want something that is unsupervised. We don't have access to the labels, and you see that we achieve that. We want something that is adaptive. Why do we need something adaptive? We want to be able to account for inter-individual variability. So if we have two person doing the experience, the system needs to adapt to each of them. Okay, this is what we call inter-individual variability. So I wear the BCI headset, someone else wear the BCI headsets. Even if we're aiming for the same feature, there will be some slight difference between them. Okay, so this is inter-individual variability. This is why we need adaptation. I'd say that this is the topmost reason in this case. And then we also want something that will fit and adapt to non-stationarity. So if I do an experience that lasts for, let's say, 30-45 minutes, some of the features might change a little bit over time. For various reasons. So adapting to non-stationarity means that even if the characteristic of the feature, this is generally a limitation of explicit calibration methods. So they will calibrate the system early and during the experience, but as the experience goes, people tends to shift a little bit the mental states, and then what has been calibrated early on is not necessarily as good when the experience drags on. So we want something that will keep on adapting, keep on improving as the experience goes, and react if something change in the mental state. We'd prefer something relatively simple. Try simple thing first. We need something that is sufficient, that works well. We don't need to over-engineer, over-design the system. And ideally, we also prefer something that is tractable, interpretable. That is, if we use a complex algorithm, sometimes it becomes a black box. That is, it works or it doesn't. But when it doesn't work, you don't know why. You know, so especially when we start with simpler hacks, we want something that we can debug, something that we can understand to guide us towards fixing the issues that we notice. So we want something that is tractable, interpretable, that when we see the results, we understand how the system got there. So this is the objective I set for this demonstration. This is general machine learning complexity trade-off. It's just like a general thumb rules that you have when you do machine learning. So simpler models will generally, especially parametric models, will generally be more robust, okay? But more robust if sufficient. That's always important to say, because simpler models are not as good, don't have the same potential as complex models, but if they're sufficient, they're generally more robust to outliers and bad data, or even data unbalanced data sets. Generally, simpler models require less training data. This is what we want here, something that requires much less training data. Simpler implementation, okay? No linear regression, which technically is the simplest model ever, has only two parameters to fit and can fit within a few lines of code, 3 or 4 lines of code. A deep learner needs a full module and a whole system to be implemented. So generally, simpler model, we have simpler implementation, but we have to always consider that more complex model will have better predictive power generally. So it's really an idea of like it's a trade-off, and the idea as a machine learning engineer is to find what is the simplest model that is good enough for the job. That's always what you're doing when you pick machine learning algorithms. Just a quick reminder of what we're working with here. So we have the Muse 2. There's a bunch of, there's 4 sensing electrodes, so TP9, TP10, and frontal AF7, AF8. In regard to the alpha wave, we are interested. The alpha wave originates from the occipital lobe behind the head. So we will be focusing on TP9, TP10. This was already validated by me offline when I was looking at the signals and the different channels. So TP9, TP10, this is what we'll be using to sense the alpha wave. So those are the 2 channels we'll be using for this experience. This is the results from that we got at episode 2, and what we see here is eye open, eye closed. We see that when we close our eyes, we have this bump here that appears that shows that this is the alpha wave between 8.5. In theory, is between 8 and I think 12 or 13. Okay, so this is the shaded region. This is the alpha wave, 8 and 13, yes. And of course, someone could say, hey, look, your peak is a little bit more towards 11, so I could restrict a little bit the range of frequencies, but I want my experiment to work with anyone. And from one person to the other, the alpha peak might shift a little bit. Okay, so the idea, let's keep it, let's use the theoretical band for the alpha wave, and this is the signal that we want to capture. This was picked up with the Muse. Okay, the signal to noise ratio could be better if we were using a different device, but with the Muse, this is what we're working with. Now, offline, okay, before the video, I did some trial and error to find out what is the best way to what is the best statistics to use, the best feature to use, basically, and the one that provides the best statistics for what we want to do. And what I found is that relative alpha band power is the best feature to model. So the way to do it, so I'm skipping today over the 2 seconds window sampling. So I take the whole time sequence and I break it down into 2 seconds windows. We'll see that in the next episode. When we'll do the real-time paradigm, I'll explain this part. So I generated a bunch of samples through this, and what I compute for each sample, the relative alpha power. So what you do is you compute the power in the alpha band, and you compute the sum of the power of all frequency bands, okay? And you divide the alpha band by the sum of all power. By doing this, you ensure, by the way, that your feature is necessarily between 0 and 1. Okay, necessarily, because if there's only power in alpha, it's going to be 1, and if there's no power in alpha, it's going to be 0. So it kind of restricts your feature. It normalizes it, okay, so it makes it more trackable, it makes it easier to work. So through my test, I found that relative alpha power is the best feature to model for this experience. I'm computing the average of the relative alpha for TP9, TP10. In my experience, I found that TP9 is actually better than TP10, but because I want this to work with everyone, I want to get the robustness that comes from sampling 2 electrodes instead of building the experience around a single electrode. So even though it's a little bit, the performance is a little bit less good, I prefer to use the sum of both electrodes instead of using a single one. So this is a feature that we want to work with for the experience. Now, the modeling approach we'll be using first is, I said it earlier, it's parametric modeling. Parametric modeling is when you make some assumption about the distributions or the feature that you want to model. Non-parametric modeling is one where you don't make any assumptions. Okay, so that's kind of like the idea here. I want to use the standard normal distributions. Now there's a few reasons here. It's not the best model. Okay, I'll tell you it's not the best standard distribution. I'll give you the answer, I think, next slide. But the standard normal distribution is a distribution that is very easy to work with. There's many tools to work with. It's a very well-defined distribution. There's many analytical solutions. And it's generally good enough for many applications. Not all of them. You always need to ask yourself, what is the cost of using normal distribution if it's not truly a normally distributed feature? But for the current experience, I show you some data here. So this is real data that we'll be working with. This is the eye-open data. So I fitted a normal distribution over it. And you see there's a little bit of the distribution is slightly skewed. Okay, we don't have that many samples, but already we see there's some skewing that takes place here, where the distribution is a little bit heavier on the left side than on the right side. There's a little bit of a tail here, so you see the data goes a little bit longer here. Here it's bounded. Okay, the fact that it's bounded already tells you that it cannot be a true normal distribution, because the normal distribution is unbounded. So there's a bound at 0. It cannot go in the negative range. But you see that even though it's not truly a normal distribution, the fit, I guessing it's not too bad. I'll tell you, the real answer, even though it's not the real answer, but generally if you do a power band ratio, you should find a non-central F distribution. This is the theoretical solution to the problem of fitting a power band ratio. Because EG is pink noise. Okay, so I'm not going to go further down here, but this is the idea. But you see, even though the true solution is a non-central F distribution, a normal distribution is good enough for the problem we want to do. And the benefit is that it's much simpler to work with than a non-central F distribution. If I got to say, by the way, you'll see the name of the files here, because I remember in the description you'll find the link to the GitHub. In episode 3, you'll find combine all the files to regenerate these graphs and these results, as well as some sample data. So if you want to reproduce this, you have all the data here. So so to get this, you run offline data analysis. Okay, so this is the modeling approach we'll be using. So we'll use a standard normal distribution. Now, when I designed this experience, I had two ideas in mind. The first that I had was to build a two-states modeling using a Gaussian mixture model. I actually worked all my way through the Gaussian mixture model, but then I said, no, given that it's a YouTube video, I had the feeling that the one-state z-score could work as well, and I did it. No, so basically, because it's a YouTube video, I want people to learn from this. So I say, you know what? I'll just redo the whole thing with a one-state z-score. So we have some, so we can compare both models. So we'll see both models, how they work here. I'll explain both of them. I had good results with one-state z-score on other experiences. So it's not worth, so we'll see both. So if we compare, so just like here, just from my knowledge about these two models, I kind of build this kind of like a table here to see. So in terms of robustness, I would expect the Gaussian mixture to be a little bit better, because the true system, eye close, eye open, is inherently a two-state system. Okay, so with the Gaussian mixture, we will try to fit these two states. The model simplicity, the one-state z-score is definitely simpler because we're fitting a single distribution. The implementation is also simpler on the one-state z-score, but let's be fair, the Gaussian mixture is not that complex either. Okay, we're not dealing with a very complex model here, and obviously I worked with the GPTs, and ChatGPT was able to, with one query, was able to generate both models entirely. So so implementation was not a challenge here. Predictive power, Gaussian mixture is definitely better here, because it's a little bit of like it becomes an unsupervised classifier. Basically, that's what we build here, while the one-state z-score is not inherently a classifier, or at least it's not as good. And I had personal interest with the Gaussian mixture model because it's a little bit more challenging, and I wanted to see, recently I built a one-state z-score for a different problem, and it was very fresh in my mind of how it was going to behave. So I was personally interested in Gaussian mixture models. So this is why I preferred the Gaussian mixture model, but like I said, I built both for this video. The z-score, option one, the way it works is basically, this is theoretical data, but what we do is we do have two classes, but what we do is we fit one distribution over all the data. And then we used, because we have the mean and the standard deviation from the results from fitting the data, you can transform it z-score each sample. Z-score tells you, so if you have a sample that lands straight on the average, the z-score would be 0. If you have a sample that lands one standard deviation above the average, you'll get a z-score of 1. And if you're one standard deviation below the average, you'll get a z-score of -1. So you see, so it kind of like builds this transformation function where your samples are no longer represented according to their absolute value, but rather to their z-score value. And for many situations, if you have a one-state systems and you just want to know your sample, how far it is from the mean, this is a very good transformation. And this is the online normal estimator, the way it works. So we'll run our data, okay, over each sample. Samples are 2 seconds windows, and over time we try to best estimate the mean and the standard deviation. Now, I should have started with a different prior, but the idea is you see from the prior hypothesis where it lands. We'll see it more with the Gaussian mixture model. So this is our first model that we'll be using. It's called we call it the z-score transform. The Gaussian mixture model on the same data instead assumes that there are two distributions, and we'll try to fit two distributions over the samples. I remember you guys. It is not, it is an unsupervised model. Okay, so there's a logic here. So every time a new sample here, you look at it, you say which one is it the most likely to belong to, and then you add the sample to this distribution, and then you update the parameters of the distribution. Now it's not bulletproof. Okay, if your prior parameters are not tuned, you are at risk that all samples will fall into one distribution. Okay, but if your priors are not too far away, it will manage to fit parameterize the two classes distributions. So this is the Gaussian mixture model. Now here we have a better demonstration of online fitting. So I started, the green one had the prior of an average of 1, and the red one had the prior is like the prior parameters. It's your assumption when you start. Now I obviously pick 0 and 1 to create this to maximize the effect, and you see I sent a bunch of random samples, and over time they both distribution found more or less the right distributions parameters. So it's an online learner that will, as the samples comes in, it will parameterize our two states, which for our case will be eye open and eye close, obviously. So those are the two models. So the normal distribution, the z-score, we fit a single distribution, and we transform samples into z-score. And this one here, we have two distributions, and now it becomes kind of like a unsupervised classifier, and you'll see how this works. So this is the offline validation. I say offline, it runs on the same data that I recorded during episode 2. Okay, so this is, you have here, the green is eye open, eye closed. Okay, so there's 4 trials. Each shaded region lasts 120 seconds. Okay, so we start the model, and it learns online, unsupervised. So the model doesn't have access to the labels. Keep that in mind, unsupervised. And you see here, for instance, when I close my eyes, you see how the model is pulled in one direction. You see it here, you see it here. Here is a basic, very basic classifier that I built simply by checking if the z-score is positive or negative. That's the only test I did, just to get like a sense of, if we use it as a classifier, we would expect to find eye open to be negative and eye closed to be positive. And we see here that it doesn't really perform in terms as a classifier, okay, at all. At all. It does have, see here, it seems like it does a little bit, maybe a little bit, but it's definitely not a great classifier at this point. If we look at the z-score, you see I said it needs to be tractable. You see we can still work, and instead of using using the labeling of the classes that I did before, we can map the z-score. And when we look at the z-score, we get the sense that it's a little bit better than than gave us. The red line, by the way, is just a smoother, so it reduces the noise. The red line is very easy to implement, so we would probably work with the red line. It's a smoother version of the black line. We do see that it works a little bit, but it's definitely not great. Now, this is the online GMM. Online, I say online because it learns with the sample over time. But it's an offline. It runs on offline data, pre-recorded data. And now we see a little bit of how it works. First, it's definitely better. We see this one here is not great. Okay, we see that this sample here is not great, but it could be because the signal to noise ratio for this specific trial was not as great as the other one. But for the other ones, keep in mind, even here, I closed my eyes before the region. So the instructions was given right there. So generally, I close my eyes ahead of time. So this is why we see that it goes there. And it definitely works better. You see, even with the smoothing version, it's almost perfect here. And we see also, remember here how the model is being pulled in one direction, especially here, we see it a lot. Well, you see now, when it's being pulled, it pulls one of the distribution more than the other. This is where the Gaussian mixture model is more robust, is that if you have many outliers or many samples that are outside the currently modeled bound, it will only bring, or at least it will bring one of the distributions much more strongly than the other one. And this is what grants it a lot of robustness. And you see the priors were 0.3 here and 0.5 here. It was intended that I use these priors, that I could have used the priors that were computed from the data, but I didn't want it to be spot on right away, to give the model a chance to show its adaptation capability. So this is what I did here. And now it's not perfect. It's not, keep in mind, it's an unsupervised classifier. Okay, I treat it as a classifier, but truth is, it wasn't trained on annotated labels. It was trained on just like data coming in, and it forms its own representation from the data. Obviously, it would perform much better if it was a truly trained supervised classification process. So now we've compared the z-score and the GMM. Obviously, the GMM wins the cup here. So this is the one we'll be working with for the part 2 of the video, when we'll do proper online biofeedback. Keep in mind that there are a few limitations here. First, we are not trying to reject artifacts. This would definitely improve the system as a whole if we were to detect and remove some samples. So we'll work in that direction, but later in the series. For now, I want to keep things simple. GMM convergence. Now, if we don't start with good priors, there's a way for the system not to work. I did a test that I'm not showing here, where the prior was 0 and 1, and run it on actual data, and it didn't converge because the prior of 1, the distribution that started with an average of 1, didn't receive enough samples to converge. I'm pretty sure that it would have converged over time, but it would have been much longer before it converged. We don't want that. We want to start with better priors. We're working a very small data set, keep that in mind. It's good enough for now. We will need, but a larger data set will be used to do a proper evaluation of how the model performs, especially at the population level, when we have like many people trying the experience. In conclusion, it's a good starting point, the GMM. It will require more validation when running online, but this will be our starting point to build our real-time experience in the next episode. So part 2 of the video, which will come up shortly, we will take everything we learn now, okay, and we will turn it into a real-time paradigm where we have proper auditory feedback. Why I did it in 2 parts? The main reason is because I want to keep these videos bite-sized. Like, it's already been 30 minutes. And I try to, can you believe that? I try to make them 10 minutes. And also it's I always start, any systems that I design will start with a offline design, offline test. It helps to make sure to de-risk, understand the data. You can do lots of trial and error much more efficiently with this approach of doing offline design. And then once it works with offline, in the offline scenario, then you turn it into a online scenario. And then you deal with the complexity of making it work in real time. So next video, we take everything we learned today and we turn it into a proper real-time paradigm. So you'll see brain-computer interface in action in real time with auditory feedback. The link in the description to the Discord, to the GitHub. GitHub has all the code for all episodes, so you can go there to grab it, and it should run as is. If you have any questions, come on the Discord. I provide some supports, or community will help you to get through the examples. And this is it. I hope you enjoyed, and I'll catch you in the next video. Okay, bye-bye.